Right. Well, I'm Luke, and this is James, and my role is I'm a visualization software engineer,
And I'm a machine learning engineer.
and we both
Sorry.
work. Sorry, you.
Keep going.
Yeah, we both work at a company called Axial 3D, just in the city centre. It's focused on medical 3D printing, and I think initially this talk was going to be more focused just on like the rendering side of things that I do, but then later on, kind of James came in, and it's going to be more of a collaborative thing, talking about our entire pipeline, how we get from scan data we take in from a hospital to a completed 3D model.
So models like these.
Yeah.
But we'll talk about them now.
So So just quick overview of the company. We kind of just described it before. Yeah, we take in DICOM format medical scan images from machines like MRI and CT scans, and we use those to produce meshes, which act as the basis for these 3D prints, which then are used for preoperative or intraoperative planning. So for surgeons to use to like plan out what approach they're going to take when operating a particularly difficult case. And do you want to?
Yeah. So, as Luke said, the basis of these models is to help people plan surgeries. So the first one, I guess, on the left, in terms of these images here, it's a scoliotic spine, I think, of an 8-year-old. So this was a particularly bad case where just looking at the 2D images wasn't sufficient to plan out the surgery. So this model was used to help plan the implantation of metal rods into the spine to help correct it. This one is, I think, our most famous case. So this is a kidney. And this was used in an operating theatre to help plan the removal of this black tumour here, which was absolutely necessary for the tumour to be transplanted into another patient. And then the model you see on the right is just a foot, and that was the model was used to help verify that the red metal mesh there, well, it's not red in real life, but that the metal mesh was placed in the correct position. So just so you get an idea of where we start from, these are the two modalities that we see at the start of our journey that Luke was talking about. So the one on the left, your left here, is a CT scan. And CT scans work effectively on the basis of firing beams of ionizing radiation through a patient. And what we do when we fire the beam through the patient is we measure how much that beam has been attenuated on the other side. And by seeing how much it's been attenuated, we can identify what kind of tissue that's passed through. So obviously, I guess attenuation is going to be more affected by dense materials. So bone in particular is really well picked up, whereas you don't see in that image good distinction between the softer tissues in the brain. So when we want to construct bone models like we have in the foot or the spine, we would use CT. And when we want to look at soft tissues, we use a different modality called MRI, and I'm sure you're all used to both of these in some sense. MRI doesn't rely on ionizing radiation at all. It relies on effectively just firing putting a patient under the influence of a magnetic field and waiting for the protons in the hydrogen in your body to align in a specific way. And you can measure that kind of alignment and use that to pick up what tissue it is or you're looking at. And of course, then the softer tissues are going to have a lot more water than bone, and that's why you tend to get better contrast and better resolution for these kind of materials.
So just going to talk you through the process how we get from those base images to a model like that example, which I'm going to keep referring to continually throughout this. So segmentation is step one. So this is probably the best quote I could find to just describe how that process works. It's the task of decomposing image data into meaningful structures that are relevant for a specific task. And that's from a book, Visual Computing for Medicine. So in our case, the meaningful structures are anatomical structures like bones or organs or blood vessels and whatnot. And our task is we want to be able to have a 3D mesh for 3D printing. So just in case it wasn't entirely clear from this image, so these are cross-sectional cuts of a section of a patient's body. So
they're 2D.
Yeah, 2D. So you basically work your way up along whatever given axis you're choosing along the patient's body, and you take these slices, and that way you can build up a three-dimensional volume by layering them on top of each other in what we call a stack. Now, if you just wanted to see what that looked like, that 3D shape, you could just take all the collected pixels from those 2D layers and create a kind of three-dimensional array of that and render it using a volume rendering technique, like a point cloud, and be able to see like an approximate distribution of that in 3D and see what that looks like. But it's not, aside from visualization, it's not that flexible an approach, like using a geometric mesh where it's actually the models are represented as points in space building up faces that make a polygonal shape. That's a lot more flexible to operate on in in a virtual space and to use as the basis for a 3D print. So in order to do that, we need to first go through this segmentation process. So I'm sure people are used to the notion in computer vision of if you want to pick out an object in an image, just detect it's there or detect its boundaries. That's not that unusual a notion, I would think, but it's a bit more of a thorny issue in medicine just because, again, we're dealing with cross-sectional images, and each of these two-dimensional shapes throughout a 3D structure, for example, in this case the brain, can look very different depending on what axis and what height you're at. And in addition to that, that's presuming the best case scenario where it looks like a normal version of that organ as opposed to a grossly deformed version that could be the result of whatever accident a patient's undergone, because typically we're getting scans of patients, if they're in a hospital, there's something wrong that we need to...
Don't come to us if you're perfectly healthy.
Yeah. So I'll just walk you through how segmentation works. So we need to define very clear boundaries between these shapes in order to act as the basis for constructing these meshes. So I've gone through that. So there's a few different ways of doing this, and there's a few different criteria we use to assess different solutions for segmentation. So how robust is the solution? So is it applicable to numerous or every potential case? If you need to have a different approach for, say, blood vessels versus bones versus different organs, that's not ideal because you don't want to have different workflows that people need to learn. It takes up a lot of time and effort. So you want as universal a solution as possible. Accuracy, you want your boundaries to be as close as perfectly possible to what the actual physical shapes described in these images. Otherwise, you could it makes a significant difference if you're making decisions for a surgery based on these, because it could be the difference between someone living or dying. Reproducibility, you want the solution to produce consistent results every time you go through it. You don't want to have slightly different or differing results, because ultimately this is meant to represent objective reality of the 3D shape, and you want it to be efficient and be able to accomplish it in a reasonable scale of time. So these are just a few examples of techniques that have been proposed. So these are the things that have kind of come and gone. So these aren't ultimately what we do internally, and James will get on to explaining how we use machine learning to accommodate this task. But so just showing originally the most straightforward way you think to approach this is if you actually had a professional like a radiologist come in to actually manually define the boundaries of a given shape. So in this case, if I were trying to highlight a section here, I'd go in and
it's not working.
Is it? Hang on.
Great.
There we go. Okay, so I would go in and I'd manually kind of draw out a pixel kind of
mask.
Yeah, mask. Yeah,
so in this case, it'll just be a segmentation of the ventricle in the brain.
Yeah, so I would just have to manually fill in that like this, and you can imagine going through this process on what is potentially a stack of hundreds to thousands of images very quickly becomes very tedious and very easy to make a mistake, very easy to lose focus, and it's ultimately just not very efficient in terms of speed. So based on those previous criteria listed, it's not very fast, and it's not necessarily that reproducible because individual people may differ in their interpretation of an image, even if they're both very experienced in a given area. So then you move on to slightly more complicated algorithmic approaches like region growing, where you start from a given pixel and you expand out, incorporating different pixels based on a given selection criteria, hopefully building up the section or area you're interested in. There's other more kind of lateral solutions like watershed, where you actually treat the image like a height map and actually then kind of fill it in as though you're filling in a physical kind of piece of terrain. So these ultimately kind of come and gone, because while they kind of get 60, 70, 80% of the way there, ultimately you still kind of need a person to come in at the end and correct the last little bit. So it doesn't really solve the problem so much as just give you a bit of a leg up to start with. So this is now we're coming into the machine learning solution.
Yeah. So effectively what Lucas said is that there's a bunch of ways that we use to do segmentation, and there's a good reason why there's a lot of interest in finding new ways to do it, and why I guess there's still a lot of continued interest. The major one that Luke said was that this takes a lot of time, and also one factor that probably doesn't seem as important as it might otherwise is that it's a really boring task to do. And if we need somebody to do it accurately, we need them to maybe not enjoy it, but to get it done as quickly as possible so that they can focus their attention on the task. So these are just a couple of like rough stats from the models that we produce ourselves, and you can see that the 3 bars on the left, and I apologize for the y-axis, for some reason it's broken. The y-axis represents hours in terms of segmentation time, and it should start at 0. So when you see the red bar for the 5th one in, you can't see it because it starts at 1.5. Sorry, it should be there. Anyway, yeah, the first 3 on the left, they represent segmentation times when done manually that take quite a long time. And there's a good reason for it. That's because they are images, or when we segment these, they are of regions, images of regions that have quite a lot of bones. In the wrist and the hand, you have your metacarpals and your phalanges in your fingers. And in your foot, you have the metatarsals and the phalanges as well. And the spine, obviously, you have all of your vertebrae. And when we use automation, which is the machine learning I'll talk about in a minute, we can significantly reduce the time that it takes to do that kind of segmentation. But you'll notice then for the 4th one in, which is for the arm, the segmentation process actually isn't that long in comparison to the rest of them. And with automation, we can't really speed it up a whole lot. And there's a good reason for that as well. And that's because the arm and other regions like it are made up of 3 major bones. This one, in this case, humerus, radius, and the ulna. And they're very well defined in most images, and there's not much ambiguity going on. In the 3 to the left of it, you have the case where when you're looking at different bones, it's going to be very difficult to interpret where certain bones stop and where other ones begin. So one important part of our process is to be able to identify individual and independent bones and segment them as separate objects. And as Luke was saying, that can also be quite a subjective thing to do. So as everybody is wont to do now, they introduce a machine learning solution to speed something up. And what we effectively want to do is take the process which we have now, and I'm going to represent purple images as our original medical images and blue as our segmentations. We want to take it from having a person do the process of doing the segmentation to having some kind of black box do it. And hopefully that black box can do it as quickly, maybe nearly as quickly as the person, and certainly as accurately. So the way we do that is by getting the expert who would previously have been doing the segmentations for the purpose of creating a product to create segmentations for the purposes of training our algorithm. So we get a bunch of medical images and perfect segmentations, or assumed to be perfect according to our experts, and we feed them into our machine learning algorithm, whatever kind of algorithm it is, and we produce these red images which I use to represent segmentations which are near perfect. And when I say near perfect, it means they still require some kind of human attention for 2 reasons. Is that they're near perfect, they're not finished, and another reason is that they need to be verified. So in order for our segmentation to be trusted, seeing as they're being used for a medical device, we need to have a human verify that they're good. So what we end up then is a process that looks like this image here, where we have our medical images, we feed them into a black box, it does the segmentation, which is then taken by a human and then corrected into a segmentation which is hopefully which will be perfect. And that black box that we use is a convolutional neural network. And this diagram, which I will show you now, it kind of seems a little bit complicated, but it's not really when you break it down into 2 tasks. So again, what we want is on the left our medical image, which we use as our input, and then on the right our segmentation maps. So a segmentation which identifies particular regions in that image that we're interested in. And we have 2 branches to this convolutional neural network. One that identifies features. So what we want to do is look at our image and say, there is a particular feature here. And at the start, we look for very simple features. So what a convolutional neural network does is it looks for very basic shapes at the beginning. So straight lines, maybe small curves, and particular types of blotches or dots. And from those features, we can keep looking at features based upon those and build up a hierarchy of features. So we can look for more complicated features, such as tighter curves, right angles, that kind of thing. And eventually, when we do it enough times and we get enough of an encoding, we can encode this kind of information in a very high dimensional space with a very low dimensional image. And that tells us, yes, these objects are here. But now that we know those objects are there, we need to obviously identify where in the image those objects are. So we have this idea of an upsampling. So we take our images now, which are very small, and upsample them into images which have the same dimensionality as the original images we started with, because we want to perform a segmentation. And all these operations are very simple operations. It's just the combination of them that makes it seem complicated. And the only thing that we need to do to make our feature network work with our localization network is concatenate those images together and then do the convolution operation, which is a fairly trivial operation in terms of computer vision tasks. And that gets us our segmentation maps, which hopefully we can produce with good accuracy. And I guess since I'm a Python developer, and I mean any sane person who does machine learning is a Python developer, there's nothing, you have to be nuts to use Julia or something like that, but people do. There's 3 major frameworks I've come across that make this easier than it otherwise could be. And the first one of those is Theano. That's a relatively old one now at this point, and I mean it's nice enough in terms of it's a package that does automatic differentiation for you, so there's that to like. But the 2 on the bottom, Keras and PyTorch, are the ones that, at the moment, which are kind of at war with each other for, I guess, or usage. But they have 2 different really applications. Keras is basically a wraparound TensorFlow, which makes TensorFlow easier to interact with. TensorFlow is famously painful to work with because of its static graphs, and Keras effectively makes it nice to build those graphs like I had in this image here. And the nice thing about Keras is it's focused on deployment like TensorFlow is. So once you train a model and build it in Keras, it's very easy to take that model and then put it into production. PyTorch, on the other hand, it's probably even more beautiful than Keras, and it's my favorite one, which is why I have a PyTorch sticker on the back of my laptop, and it's the only one I have. But it's not so much focused on deployment. So while you can make really cool models with PyTorch, actually getting them onto somebody else's machine is a pain, and it might not be worth it. So just to illustrate how easy it is to build a network with Keras, this is an example of a simple convolutional neural network for classification. So this is a different task of segmentation, where it's just, for example, taking an image and identifying, again, whether maybe, I don't know, there's a dog or a cat in it. And if you ignore the import statements and the variable definitions, you can build a network that does this task really well in about 9 lines. Of course, you need the data for that, and you need to train it, but I guess that's...
And you need to know what layers to put in there, which is not trivial.
You can wing that, I think. With our models for segmentation, they turn out to be quite large because we need them to be accurate, and that's probably one of the easiest ways to make them accurate. So this number represents the number of minutes on a CPU it takes one of our models to do inference on a stack of images. So our models are so big that it will take 40 minutes to produce a prediction that will then go to our operators to clean up. 10,000 is the cost of a Tesla V100 GPU, or $10,000. So obviously CPUs aren't going to work out for us, so we have to accelerate this process somehow, and that's the way everybody does it. Unfortunately, though, we have this many images to train on. And when we have that many images to train on, and we want to see them multiple times, it means we're going to be doing quite a lot of work, and we need a fairly big and comprehensive machine to do this for us. And that's the number of parameters that one of our latest models has in it. So you can buy these machines and you can build them yourself, but why would you? They're very expensive, and at the end of the day, you're not going to be using them for that long anyway. You train for maybe a few days, and then you put your machine away and you evaluate the results for weeks after that. So what you end up doing is you use something like Google Cloud Platform or AWS to do your training, and that makes it really nice because then you can spin up any machine you want, you can have as much RAM as you want, you can attach any GPUs to it that you want, and it basically means that you get a huge time saving, especially for something like, if anybody's done it before, trying to set up the NVIDIA CUDA drivers on your machine that have already been set up. That's the amount of time you end up saving. Okay, so once all that's said and done, you get your segmentation. So this is just a segmentation of a CT scan. And our model produces a fairly good identification of where the bones are. So in blue is its consideration of where it thinks with over 50% certainty that there is bone there. And the most important thing about this, as I said earlier, is that it resolves these bones as independent objects. So there's a good separation between them, and that means that hopefully it's going to take our operators less time to clean up this segmentation and get it into a 3D model. A more difficult task is segmenting soft tissue and MRI, mostly because MRI takes longer to acquire. And what that means is you get lower resolution to make this clinically acceptable in terms of having a patient inside the scanner. But still, we can get models that actually do quite well. So in this case, on the left, we have segmentation of the blood chambers and the blood vessels. And on the right-hand side, we have segmentation of the myocardium, which is the muscle that sits around the bottom of the left and right ventricles. And believe me, that is really painful, and it takes quite a lot of work to get a good segmentation there. So I put this image up because I'm really proud of it. But, as Luke was saying, the vast majority of the work that it takes to get a model from doing an okay segmentation to a decent segmentation, or a really, really good segmentation, is getting it from a very high percentage. So if our model's at 90% already, or let's say even 95%, more work is going to get it, go into getting up the extra 5% than it took to get it to 95% in the first place. That's because we have to identify very subtle features that humans are very good at, but machines are very bad at. And what this image illustrates is, with the green line, is our accuracy for the segmentation along that particular slice. So along where the bone is, or where the thick bones in the arm are, you can see that the accuracy sits somewhere around 99%, which is the right-hand y-axis in terms of this whatever accuracy score we've used here. And then when you get closer to the joints in the bones, you start to lose that level of accuracy. So our task now is to take the work that we've done and hopefully get it to the point where we have a straight green line across the top. And that would be a model that was, I guess, nearly at the point where we don't need human interaction anymore.
Yeah, right. So I've been rambling on about segmentation and machine learning for quite a while now, and it maybe seems like how does it have anything to do with the models that we were talking about at the end of this process? That where have you put the you just disappeared the kidney, or is it around there?
It's around there. Sorry.
Okay, yeah. What does any of this have to do with this final shape? So everything we've talked about so far has just been about establishing this clear delineation of these structures, and now we can get on to the actual extraction of a 3D mesh from that. So that's like isosurface extraction is the term referred to, and a lot of the algorithms that accomplish this. So what you see in here is like a nice animation I found of just illustrating how a basic marching cubes algorithm works, where it will march through each of the little voxels that made up that 3D space of pixels, and it will insert individual faces where it determines there is an intersection of the inside and outside a given boundary. So there's a few different algorithms. There's actually quite a few different algorithms you can use to approach this task, and you might wonder, well, if everything we've done before was about ensuring that accuracy, what difference does it make what algorithm we use here? But ultimately produces the same highly accurate model, and the difference would be that. While that is the main factor we're concerned with, the accuracy in terms of its how it relates to the actual physical shape described in the images, there's also things to factor in, like say the file size as dictated by the number of faces, and there's potential to describe an accurate version of that same shape with less or more faces depending on what way you've accomplished that reconstruction. So it's just a relatively short list of the amount of different approaches you can take to this, and I won't go into all the different algorithms because there's quite a few and they can get quite dense and quite convoluted. So just to give a brief overview of some of the approaches we've kind of iterated over to try and find what the best way to do this is. But after that process is completed, then you have spat out, and this automated process is spat out a model that you can then start to edit for the specific needs of a client. In this case, usually a hospital or a surgeon in particular that needs certain things highlighted, say different sections, like different colors. In this case, like the tumor has been highlighted inside this transparent section in black. Certain things need to be added, like say the company logo and the product details are embossed here. Other things like that need to be done, and at that point you have a mesh that is ready for printing, and that can then be just verified by some software that correctly prepares a model for that process, and then that goes through the machine, and you get a physical thing like this, which then has to be post-processed by hand by someone. And after that, that's the end result of all that convoluted process. So there's lots of software that accomplishes all these individual tasks on the market. I was hoping to find a few more logos that I could just have this just overflowing off the page, just to get across that there is just so much of these things. These are just some examples of some things we've come across and maybe potentially used internally at some point. But the point I'm trying to get across here was that while there's software that covers each of the individual steps, there's nothing that covers the entire pipeline. And most of the existing companies or institutions that do this kind of work, like say hospitals or 3D printing labs, they tend to kind of cobble together their own kind of makeshift solutions, but from these different open source and closed source solutions, and it can get very it's just never very consistent or reliable. And while they can get it to a point where internally it's very foolproof and they can get good results out of it, when you start to interact with any other entity like an end user or an end client, all that breaks apart, because their notion about how this pipeline works can vary so wildly. So our solution to this, or like what we've been attempting to build for the last while, has been a unified web-based pipeline that accomplishes all these tasks in a single kind of workflow that a person can use without any kind of great expertise in one of these individual steps, and they can still complete and produce a very high quality final product. So I was hoping to have more screenshots of this, but this is just one of the single steps where we're verifying some of the DICOMs we received, and this is just like an overlay of a heat map of certain feature detections happening. So that's kind of what our overall aim has been for quite a while now, is just to make that process routine and straightforward and really something that anyone can carry out.
Yeah, the motto of our company at the end of the day is to make medical 3D printing routine. Our CEO was always saying that because I guess what inspires us from day one to the time we finish making these products is the fact that not only can we say that these probably save lives, we actually know that they do, because there's cases we have now where without these the patients wouldn't have survived. So I mean, yeah.
So just
thanks. Just in terms of acknowledgement and thank yous, I get funding from Intertrade Ireland and UCD, so that's great. Thank you, and I guess thank you for all of you for letting us speak here, and also for listening to us ramble on.
And in my case, I get a lot of funding from both Ulster University and from Innovate UK as part of the KTP program. So pretty much equivalent to James's sources of funding.
Yeah. So sorry. Any questions if there's? Yep.
How much experimentation did you have to do in terms of, I think Mark brought up the things with the layers and the filters and the filling, and because it takes a long time to build these models. So how did you go about that, or did you just say, well, let's try this, see what happens, let's try something else, see what happens?
You'd be surprised. It turns out that the model we use, and that's the model that I actually have in that image, or that I had that kind of procedural image for, that's a UNet model, and we've experimented plenty with the number of layers and the number of filters in those layers, and it doesn't seem to be that's the confounding issue. What is the issue tends to be things like your parameters for pre-processing, like the normalization of your images, or not the obvious one, but the common one, the learning rate. That's primarily because I guess the problem we have with our training is that our images are very biased in one respect, and that is the bone images, for example. It doesn't look like it, but 1% of those images is usually occupied by bone pixels, and the rest of it, the 99%, is background or other tissues. And that means our data is very biased towards just saying, well, there's nothing here. And what we found is that without proper normalization, and without a very low learning rate, a lot of the time our models will just go, there's nothing here. And it does that because it gets 99% accuracy if it does that. And it's much easier to learn that than it is to learn very complicated shapes. So if you use models like the UNet, it doesn't take that much experimentation at all.
Sorry,
Okay.
the last image you showed, what was that? What part of the body was that?
Do you remember that one?
So this one is, play that.
Go back to the beginning actually, just so we can see. This was a deformed rib case, wasn't it?
Yeah, they look like ribs.
Yeah. Yeah, so we get a lot of scoliosis cases, and this was. Is this one of the recent spines? Wasn't it?
I don't know.
Yeah. It's hard to recognize.
Yes, those are. Is that a scapula?
Yeah.
Yes, it's up here.
I remember this is the largest one. This is the one that had the jaw as well.
Yeah.
Yeah.
Yep.
Find yourself coming under like medical device standards and stuff? Is that a large part of your company has to operate and be mindful of as you create these models? And
It's not so much medical device standards as it is patient data, because we've kind of been able to kind of skirt around a lot of the actual like hardware limitations and stuff, because we only kind of come into the process after the base images have been produced. But the issue there is that the DICOM format, which is the standardized format that all this scan data comes in as in these individual slices, includes a lot of metadata about the circumstances of the scan, the patient, what their conditions were, loads of personal information about both the staff that are handling the case and the patient themselves, and all that needs to be ideally scraped out and done away with before it reaches us. But we need to take a lot of steps to be compliant with data security laws in terms of making sure that that process happens on our end. If the people on the other, if the people sending this data aren't thorough enough to accomplish it themselves.